So this is going to be our final lecture in the third section of the course, which has been on online algorithms. So we're going to culminate in this section with a discussion of the online bipartite matching problem. So let me just quickly remember you what that is. So it's going to be bipartite matching. So there's a left side, call it capital L, a right side, call it capital R. You know the whole left side up front. Okay, I tell you that before anything starts. It's the vertices of the right side that come online, one at a time. Okay? When a vertex on the right-hand side shows up, it shows up with all of its incident edges. It's a bipartite graph, so all the incident edges go back to capital L. You want a matching, you want a big matching. The rub is that you can only match a vertex on the right-hand side at the moment it shows up. You can't delay and wait to see who else is going to show up and then match it later. Okay? So that's the definition of the problem, and the goal is just to compute a max matching. Okay, so there's no edge weights, just max cardinality matching. You'd like that to be as big as possible, as big as the max matching in hindsight after you've seen all of the right-hand side vertices. So any questions about the problem? This is what we had last lecture. Last lecture, I also sort of told you about a killer app of online bipartite matching and web advertising, the interpretation being the left-hand side vertices, which you know up front, those correspond to advertisers who have purchased a certain number of targeted ads, and then people, potential customers, come in online, like as soon as they type in a search query or as soon as they view a content page, and the edges correspond to the potential consumers on the right-hand side who match the targeting criteria on the left-hand side. Okay, so it's one reason why this problem's gotten a lot of attention over the past, 7-8 years or so. A couple quick announcements. Problem set number 3, as I'm sure you know, is due Tuesday. I posted the 7th exercise set. And then my office hours, they're normally 3 to 4 today. There's a talk I have to be at, so they're going to be at 4 to 5 instead. Okay, so one time only. My office hours will be 1 hour later today. Okay. All right, so we'd like a good online algorithm for this online bipartite matching problem. So we'd like a good competitive ratio. Okay, so we'd like to always produce a matching which is almost as good as what we could have achieved with full hindsight. So what kind of competitive ratio can we expect to attain? So remember last lecture we saw online scheduling, we got a 2 competitive algorithm. We studied the online Steiner tree problem, we got a log k competitive algorithm where k was the number of terminals. So here we're trying to maximize, so we'd like to get as close to 1 as possible. And so an example that we went through briefly last lecture, I'm going to go through it again. And so what the lecture shows is that with deterministic algorithms, you can't beat a factor 1/2. You cannot have a competitive ratio strictly closer to 1 than 1/2. Okay, so no deterministic algorithm has competitive ratio bigger than 1/2. All right? It's a very simple example that shows this. So you're going to start with 2 vertices on the left-hand side. Right, so you're thinking about some arbitrary deterministic online algorithm. A vertex shows up on the right-hand side, connected to both of the vertices on the left-hand side. Okay? So the online algorithm, it now has to make a decision. Okay? It can match it to neither one. Okay, but that would be a disaster if this is the only vertex that ever shows up. Or it can match it to the top vertex or to the bottom vertex. Okay? And the point is, no matter what the online algorithm does in the first step, there's a vertex I can feed it in the second step so that it regrets what it did. So for example, if you have an if the algorithm in question picks this edge to match, then what I'll do, sort of nefariously, is define the second vertex so that its only neighbor is to the one that you already matched to. Okay? And then that'll be the entire input. All right? So the algorithm will just have a matching of size 1, whereas clearly a matching of size 2 is possible. Obviously, by symmetry, the same thing is true for deterministic algorithms, which pick this edge instead in the first step. Okay? So no matter how smart you are, just because you have to make this decision at time step 1 without knowing what's going to happen later, deterministically, at least, you're going to be off by a factor of 1/2 at least. Okay? So algorithm equals 1, but opt equals 2. Everyone clear on that argument? Just a simple adversary argument. Okay, so this raises a couple questions. Question number 1 is, can we achieve 1/2? Is there a matching positive result with a deterministic algorithm, say? And then the second question would be, can randomization help and allow us to beat the 1/2? Remember, for example, that when we talked about online decision making, it was totally crucial that the algorithm had used randomization. Remember, we had a lower bound for deterministic algorithms with respect to the regret benchmark. So we're used to the idea that randomization can help with online algorithms. So the answers to both those questions are yes. So you can get a 0.5 with a deterministic algorithm. That's a pretty easy result, which I'll show you next. And you also can beat 1/2 with randomization. Okay, and I'll give you the main ideas of that in the remainder of the lecture. All right, so as far as the matching positive result, all you need is greedy. So greedy has competitive ratio 1/2. What do I mean by greedy? I just mean when a vertex shows up on the right-hand side, you look at its neighbors. Obviously, if all of its neighbors are already matched, you can't do anything. But if at least one neighbor is unmatched, you match it to an arbitrary unmatched neighbor. Okay? So that's the greedy algorithm. And the claim is this always will output a matching with size at least 1/2 of the maximum possible. Now, this is actually pretty easy to prove directly, but that's not what I'm going to do. Okay, so I'm going to give you a more sophisticated than necessary proof of this claim, because this argument will generalize usefully when we talk about beating the 1/2 with the randomized algorithms. Okay? So the way I'm going to do it is actually by duality, so weak linear programming duality. So let me remind you what the primal and dual linear programs look like for the max cardinality bipartite matching problem. So for the primal, right, so the semantics are here is we're thinking of XE being 1 for an edge in the matching, XE is 0 for an edge not in the matching. We want to maximize cardinality. There's no cost, notice, just maximize cardinality. What are the constraints? Well, we're not insisting that it's a perfect matching. We're sort of hoping we compute a perfect matching, but it's not a feasibility requirement. We just want it to be a matching. So that means for all vertices on either side, if we sum over the edges incident to the vertex, at most one of those should be in the matching. Okay? And then these should be non-negative. All right? Now, there's a few minor differences between the primal dual pair we looked at back when we were talking about bipartite matching, because back then we were thinking about the min-cost perfect matching problem. Okay, so here there's no costs, and there's no need to restrict attention to perfect matchings. So you see the two differences. Instead of having a min in min-cost perfect matching, we have a max. And instead of having equations here, which is when we're insisting on a perfect matching, here we just have inequalities. Those are the two differences between this primal linear program and the one we talked about a couple weeks ago. So the dual is basically the same as what it was before, although again with just some minor tweaks. So before the dual was a maximization, but now the primal is a maximization, so the dual is a minimization. There's going to be one dual variable per constraint, so per vertex there's going to be one constraint per variable or per edge. So we want to minimize the sum of the vertex prices. And so because it's minimization, these inequalities are going to be greater than or equal to inequalities. So this is going to be a PV plus PW for all edges, VW in the graph. And in case it wasn't clear, so we're thinking about sort of the graph after we see it at the end of the algorithm. These linear programs are going to be only for the analysis. So we just run the greedy algorithm, we let it run, and then this is all sort of an ex post facto analysis of what happens. Okay? So this is for every edge that ever arrived. And then previously, because these were equations, we had real value decision variables. Now these are inequalities. So we have non-negative decision variables. Okay? So that's the primal dual pair for the max cardinality bipartite matching. Okay? Which you've basically seen before, modulo these minor cosmetic differences. All right, so why did I write this down? Okay? So we're trying to prove a positive result. We're trying to prove that this algorithm did something good, that it got close to optimum. And remember, when you're trying to prove these kinds of things, the challenge is always how do you know when you're close to optimum, okay? So last lecture, we just had a couple ad hoc arguments for online scheduling, for online Steiner tree, but we figured out how to do it. But also, if you think about it, the whole culmination of the first half of CS261 was sort of the message that, duality is sort of the ultimate answer of how do you know when you're done? How do you certify your own correctness? And as we'll see in the rest of this course, it's also super useful for proving approximate correctness. So this will be our first sort of nice example of that, today's lecture. So I'm writing down the primal dual pair because I'm going to show, the way I'm going to prove that the matching that the greedy algorithm outputs is good is I'm going to compare it to a dual feasible solution. And remember, dual feasible solutions, by definition, by construction of the dual, are bounds on what the optimal solution to the primal could be, okay? And so maybe that sounds kind of fancy, but actually, exhibiting the dual is very simple for this claim. So here's what we do. Again, remember, we've run the greedy algorithm to completion, and we're doing this sort of in hindsight analysis. So now what I'm going to do is I'm going to show you, okay, it's not quite a dual feasible solution, but it's on the right track. So for every vertex of the graph, set QV to be equal to 1/2 if V matched by greedy and equal to 0 otherwise, okay? So again, we ran greedy. It didn't necessarily output a perfect matching. Might have output something worse than a perfect matching. But so after the fact, we sort of scan through the vertices and say, well, whatever's matched, give it a Q value of 1/2. Whatever's unmatched, a Q value of 0. Or if you want, you can think about it like we actually define this dual in tandem with running the online algorithm. So a new vertex shows up. If the greedy algorithm matches the new vertex on some edge, at that point, we set the Q values of both endpoints to be 1/2. Okay, that's another way to think about it. Okay, so what can we say about these Qs? So call the greedy matching M. So the first thing to notice is that the sum of the Q values is what? In terms of M. It's the cardinality of M. Right? We're sort of, imagine defining the dual in tandem with the algorithm. Every time the algorithm adds an edge, we set the Q values to the two endpoints to 1/2. So at all times, including at the end of the algorithm, the sum of the Q values equals the sum of the edges that are in the matching, okay? We're using the fact that, because it's a matching, no one's ever going to have their Q value set twice. You're either just stay at 0 forevermore, or you're set to 1/2 exactly once when you're matched by the greedy algorithm. Okay, so here's the more important point. I'm not going to claim that the Q's form a dual feasible solution. Remember, this is the dual here. So dual feasible means the sum of the prices on the endpoints of an edge should be at least 1. So I'm not going to claim that the Q's form a dual feasible solution, but if we double the Q's, I claim that's a dual feasible solution. Okay. So I claim P, the vector defined by just doubling all the Q values, is feasible for D. So again, feasibility just means that if you look at any given edge of the graph, the sum of the P values of the two endpoints should be at least 1. So really, all this is saying is that for every edge, at least one of the two endpoints got a Q value of 1/2. Okay? If at least one had a Q value of 1/2, once we double, the sum of the P values of this edge is at least 1. Okay? So for all VW in the edge set, it's going to be true that QV plus QW is at least 1/2. And therefore, once we double, it's at least 1. So why is that true? Well, how could it be that both V and W, both QV and QW are 0? What would that mean? That would mean the only way it's 0 is if you didn't get matched. So So that would mean both V and W didn't get matched. But then what on earth were we doing when the vertex W showed up, right? So how could we not have matched W if V was its neighbor V was available at that time, okay? So another way of thinking about it is the greedy solution outputs a maximal matching. So there's no way you're going to have 2 points connected by an edge, both of which are unmatched, okay? Is everyone okay with that? So now we're done. So now we can use, so remember, the dual always bounds the best possible solution of the primal. So our primal is a maximization problem. So every dual is going to be an upper bound on how big the max matching could possibly be. So we're going to use this dual feasible solution to compare against our matching. Right, so just copying this down. Right, so rewriting this in terms of half the p's. This is the objective function value of our dual feasible solution. Yeah. Which is an upper bound on how big opt could be. Okay? And that's the proof of the claim. This is the size of the matching output by greedy. We proved it's at least half of the best possible. So it's a 1/2 competitive ratio. Okay? So any questions about that? This is an idea we'll see a few more times, where you have an algorithm. It's not, so notice, we didn't solve a linear program in our algorithm. Our algorithm is just the greedy algorithm. We use linear programming to analyze it, to prove that it's approximately optimal. We'll see that several more times, where we're looking at natural heuristics, natural algorithms. We want to know how do we prove they're near optimal. We're going to use a suitably constructed dual solution, okay? All right, so any questions about that? Make sense? Okay. All right, so that was the answer to the first question. Could we actually get 1/2, say with a deterministic algorithm? The answer is yes. So can we do better with randomization? Okay. So I'm actually not going to answer that question for you in lecture. So rather than thinking about randomized algorithms for integral matchings, I'm going to think about deterministic online algorithms for fractional matchings. Okay? So remember, in a matching, you have to pick an edge. Every vertex should have at most one edge picked incident to it. But then you can also talk about fractional matchings, right, where you can have fractions on edges between 0 and 1. So in some sense, feasible solutions that are not 0, 1 to this primal correspond to fractional matchings. Okay, so, but let me tell you that on problem set number 4, so it turns out that the same ideas I'll teach you in this lecture also lead to the same improvement for the integer matching case with a randomized algorithm. Okay, problem set number 4 will walk you through the steps to translate the analysis I'll show you today to the randomized algorithm for the integral problem. Okay. All right, so I guess one quick thing to remember. And at first you might find this weird, actually, to talk about the fractional bipartite matching problem instead of the integral one. Because wasn't one of the points a few lectures ago that the problems are the same? So this, I don't know if you remember, but when we were talking about LP duality, one of our examples is we went back to the Hungarian algorithm and we used the Hungarian algorithm to prove that actually there's always a primal solution, which is amongst all fractional solutions to the primal, there's an optimal one, which is 0, 1, corresponding to a perfect matching. How did we prove it? Because the algorithm exhibited an integral matching, but it also exhibited a dual with exactly the same objective function value. So that shows that there's always a 0, 1 optimal solution. Also on exercise set, I think number 5, I ask you to prove it directly. So for bipartite matching, there's always an optimal solution, which is 0, 1. So allowing fractions does not help you solve the problem if you're solving it optimally. However, allowing fractions can help online algorithms. So why is that? Well, let's return to our same example. Right, so we have 2 vertices up front on the left, a new vertex comes on the right connected to both. So before we had to pick, either we match it to the top vertex or we match it to the second vertex. With fractions, we don't have to pick. We can hedge. So in light of this example, it's tempting, if our algorithm is allowed to use fractions, to match this edge 50-50 to each one. Okay? That's something this algorithm could do that the previous one could not. And then an adversary can come along and say, oh, well, this one's only connected here. But then there's still 1/2 room here for us to at least partially match this vertex. So at this point, the fractional online matching algorithm can assign a 1/2 to that vertex. Okay? So opt is still 2, and we're still not as good as opt. But we got 3/2. Okay? So that's only a ratio of 3/4. Right? So it's not 1/2. So at least in this example, we're not stuck with the 1/2 if we can have fractions. Okay? All right, so any questions about that? So that's why it really is a different problem when you start talking about fractional matching. Just to kind of foreshadow what you'll see on problem set number 4, notice that, if you had to be integral, but you were allowed to randomize, there's a sort of obvious analog to splitting 1 unit fractionally on these 2 edges, which is to flip a coin and pick one of the 2 edges at random. Okay? So building on that kind of idea allows you to translate solutions for the fractional problem, like you'll see today, to randomized algorithms for the integer problem. Okay. So, questions? Yep.
For an arbitrary fractional matching, how do we know that it was actually implementable as a pure outcome?
So we're actually not going to insist that, yeah. So I mean, and as far as translating it to a randomized, algorithm, it's not obvious. It's not obvious you can do it. I'm just sort of giving you some high-level intuition about why it's conceivable as possible. But you're right. The question is, it's an excellent question. You're basically saying, so what you'd like to do is kind of realize all the fractions as probabilities over some distribution over matchings. And so in some sense, that's true. I mean, in some sense, we know after the fact. Again, just by knowing that this thing has 0, 1 optimal solutions, that kind of tells us that any fractional matching is indeed the convex combination of integer matchings. But the question is, can you sort of construct that distribution online? Right? So you need an online algorithm which actually, at the end of the day, has constructed the correct distribution. And it's not trivial. So again, the problem, as usual, will be broken down into a few steps so that you can see how it goes. But it is, it would, so last year I actually didn't lecture, but I just decided it was too much on the topic. It took another maybe 20 minutes to do the randomized translation. Other questions? Okay. All right, so let me tell you the algorithm we're going to use. And the algorithm we're going to use is really just sort of the natural extension of hedging. Okay? Actually, let me put this over here. And I'm going to call it, sometimes this is called the water level algorithm, because there's sort of a nice physical interpretation of what's going on. So the idea is you think of the left-hand side vertices that are up front as containers for water, initially empty, with capacity 1. And each arriving right-hand side vertex is a source of 1 unit of water. And what's interesting is what happens when a new vertex shows up. So when the next right-hand side vertex comes, let's call it, W. You want to try to send W's water over to the left-hand side, to its neighbors. Okay, that's the analog of matching it fractionally. So you fill up the neighbors, the neighboring containers, always preferring the containers that are currently the least full, okay, with the lowest levels. So preferring the lowest levels. So you want to think about a picture like this, right? So suppose we look at the neighbors of W. Okay, so W is the new vertex on the right-hand side. It's connected to various vertices on the left-hand side. So each column here represents the current water level, so how much water a given neighbor already is holding. Okay? And so they can certainly have different water levels. Maybe something like this. So this is a case of a vertex with 6 neighbors, all filled up to different degrees. All of this is less than 1. So now W shows up and it has this 1 unit of water it wants to get rid of. So at first, right, so basically, so you can see why it's called what it is now, right? You just sort of imagine pouring a pitcher of water into this picture and letting stuff fill up. So first it goes to sort of the lowest point. Now there's a tie. So after it's sent this much water to the second neighbor, there's a tie of the level between the second and fifth neighbors. So you just split the water equally amongst them. Now there's a 3-way tie between the second, third, and fifth, for which one's the lowest. So you send further water equally between them. And then maybe it runs out here. Maybe at that point it's actually gotten rid of its full unit of water, at which case we stop. Okay? The other possibility is that it fills up all of its neighbors to the top while still having water left, in which case we also stop. Okay? So, ends when one of two things happens. So when either, 1, all neighbor is full, or 2, W becomes empty, i.e. it has no water remaining. And if you think about a very simple example, what we did with this 50-50 split was exactly the water level algorithm, right? So this node showed up, they both had level 0, so it sent its flow equally, its water equally to the 2. This one showed up and then just sort of got rid of what it could. So when the first vertex derived, we terminated because of the second case, because the vertex got rid of all of its water. When the second vertex arrived, we terminated because the first case was triggered. Okay, all of its neighbors were full. Okay? Good. So any questions about that? So this is the algorithm we're going to be thinking about for the rest of the lecture. It's clear. I mean, I've described it somewhat informally, so if it's unclear, let me know. I tried to describe it at what I thought was sort of the optimal level of abstraction, but you never know. Okay, so before I erase this, just a reminder for those of you that came in late, my office hours today are 1 hour later than usual. Okay, 4 to 5 instead of 3 to 4. That's today only. Okay. So I hope this picture is sort of easy enough to sort of remember and store in your brain, but let me actually just sort of point out what's going to be the main property of this algorithm that we're going to use in the analysis, okay? So it's going to turn out that this algorithm does indeed beat 1/2. It's better than 1/2 by a noticeable amount, but it's not super easy to prove that, okay? So an important point in the analysis is the following. So a key property of the water level algorithm is if you look at any edge, so again, think about it in hindsight after all of the vertices have showed up. So for any edge, so let YV be V's final water level. Okay, so XE, I'm using in the same sense as in our primal. This is the extent to which one vertex is matched to another, possibly fractionally. You know, fractionally matching a vertex on the right to a vertex on the left is like sending that much amount of water. So if we sum over all of the neighbors, okay, so this is on the left-hand side. This is one of the containers. We're summing over all of its neighbors on the right-hand side that might be sending water to it. If we look at the total water sent, that's going to be the water level at the end of the algorithm of the vertex V, okay? So consider any edge, let YV denote the final water level of the container V. And then what's the assertion? So then, if you look at the source of water, W on the right-hand side, it only ever sent water to containers that had the current water level of something at most y sub v. Okay? So it's actually very simple once you can parse it, but let me just sort of walk you through it a little bit. So first of all, you want to think, so YV could be as high as 1. If YV is 1, this is a trivial statement. It just says that W only sent water to containers with final level at most 1. Okay? But that's sort of trivial, because the level can't go bigger than 1. So you want to think about YV being strictly less than 1 to be the non-trivial case. So that means there is this container. So this would be like the vertex in the upper left in that example. So it's a container which was not totally full at the end of the algorithm. It was only full up to y sub v. So maybe it was 4/5 full at the end of the algorithm. And so the claim is that then, if you look at this vertex W that's connected to V, it only sent stuff when their neighbor was 4/5 or possibly less. So why is that true? Well, think about it this way, right? So W shows up, it starts distributing its water, right? So it stops with everything it's sending water to at some common level, right? So remember, in this picture, at all times, you're sending water to a bunch of containers that have exactly the same water level. So when you get rid of all your water, there's going to be some common level, like 4/5, say, of all of those containers that you were sending water to. Everyone else who you weren't sending it to has an only higher level, okay? So up till then, you've only sent it to level 4/5 or less, and everybody's level at that point in the algorithm is 4/5 or more. Fast forwarding to the end of the algorithm, water levels can only go up, so this only becomes more true if there's more vertices that show up after W, okay? So a different way of putting it is, think about the common level of everything you're sending water to at the time that W exhausts its unit of water. The final levels of all of the things it's connected to can only be higher than that common amount at the end of the algorithm, because levels only go up, okay? So any questions about that? So this is really almost the only property of the water level algorithm we're ever going to need. Okay? So if you want, you can actually forget about the algorithm and just remember this property, though it may be easier to remember the algorithm than remember the property. Okay. Good. So how are we going to analyze this? Well, back when we had our sort of deterministic greedy algorithm, we used this dual analysis, and that worked pretty well. It was pretty easy to apply, and it gave us the correct answer. It gave us the tight bound of 1/2. So it's natural to try to copy that same dual approach for this new water level algorithm, okay? So the only difference is that now, instead of picking one edge at a time, we're sort of, gradually increasing the fraction on edges at a time. But we can try to do the same thing, right? So before, when we picked an edge, we set each Q value of each endpoint to 1/2. Now, when we increase the extent that some edge is matched by delta, we can again just sort of associate delta over 2 to each of the 2 endpoints, okay? So idea number 1, when some edge, xvw, is increased by delta, increase both qv and qw by delta over 2, okay? So just like before, by construction, inductively, at all times, we will maintain the property that the value of the fractional matching that's being constructed by the water level algorithm is just the sum of the Q values, okay? Whenever the left-hand side goes up by delta, we make sure that the right-hand side goes up by delta as well, okay? Delta evenly split between the 2 endpoints of the edge, okay? So that's good. So that's one of the 2 properties we used in our 1/2 analysis. The other property, if you think about it, back in our argument where we set things to either 1/2 or 0, we said, okay, well, Q isn't dual feasible, but if we double Q, that gives us a dual feasible P. So to get a bound better than 1/2, what we're hoping is that we can scale up the Q's by some factor less than 2. That will give us a competitive ratio bigger than 1/2 by exactly the same argument, okay? So the whole question is, we have these Qs, how much do we have to scale up to recover dual feasibility? Remember what dual feasibility means. Dual feasibility means that the sum of the prices at the endpoints is at least 1. So what we're hoping is that for some C greater than 1/2, we can prove that 1 over C times Q. So previously C was 1/2 and we were doubling. Now we're hoping C is bigger than 1/2. In this case, this is scaling up by something less than 2. Feasible for the dual. If this is true, then by exactly the same argument that's still up here on this board, okay, so if we can prove that QV plus QW is at least some C, then we just multiply by 1 over C, and we get a C competitive algorithm instead of a 1/2 competitive algorithm. Okay? So I think that's the first thing to try. So you have this new algorithm. The motivation for the algorithm is this idea of using fractions to hedge. This seems like a natural way to hedge. And so then the question is how to analyze it, and it's natural to just copy what worked before. What worked before, whenever you sort of add something to the matching, you split it amongst the Q values of the endpoints, and then you scale it up to get a dual feasible solution. Okay. All right. So you probably guessed when I wrote down idea number 1, suggesting that there's an idea number 2, that this isn't going to cut it by itself. So let me show you why. Here's a bad example. So suppose we start with 4 vertices on the left, okay? So it's sort of an extension of our previous bad example. So the first vertex on the right-hand side shows up. Say it's connected to everybody. So what does the algorithm do? The water level algorithm, what does it do? Good. Fills each to 1/4. So it increases. So basically it splits its 1 unit of water equally between all of the eligible containers, right? They all had level 0, so you just keep them all the same. Suppose the second vertex shows up and is connected just to the 2nd, 3rd, and 4th containers. Okay? So in this iteration, are we going to trigger case 1 or case 2? 2. Good. So this is similar to the previous iteration. There's 3 containers. It's going to split. All of these have the same initial level of 1/4. And so they're all tied for the lowest level. So it's going to split equally among the 3, and it's going to distribute its 1 unit of water 1/3, 1/3, 1/3. Let me use a different color for this. So 1/3 on that one, 1/3 on this one, and 1/3 on this one. Okay. So you can guess what happens, or what the graph looks like next. So the 3rd vertex on the right is connected to the 3rd and the 4th vertices. So now, are we going to trigger case 1 or case 2?
Case 1.
Case 1. Excellent. Why? Well, because this container, what's its current level? 1/3 plus 1/4. So that's more than 1/2. That's 7/12. This one's also at 7/12. So each of those has 5/12 remaining. So this new vertex will distribute equally amongst them until they both get saturated. And it'll get rid of 5/6 out of its 1 unit of water. Okay? Good. So 1/2, 1/2. And now just to add insult to injury, the last vertex is going to be connected only to the 4th vertex. The 4th vertex is already full, so nothing is going to happen on this last iteration. Okay, we just get a big fat 0 right there. Okay. So let me ask you, what's the final Q value of that vertex?
Wait, why are those 1/2? Are they 5/12?
Oh, sorry. Yeah, this should be 5/12. You're absolutely right. Absolutely right. Sorry about that. And then where's the other one? And this one, yeah. Thank you. Good. So what's the final Q value of the southwest vertex? 1/2. Good. It's full, which means there was sort of 1 unit of time overall that it was participating in increases, and it always got half of its share of that increase. Okay, so remember when we increase on an edge, it gets split equally between the 2 endpoints. So how about this one? What's going to be the final Q value here?
0.
This is going to be 0, right? Because no edge incident to it ever got increased, so it's not going to get anything. So unfortunately, what we now see is that, with this analysis approach, we would still need to scale by 2 to get dual feasibility. Okay? Remember, dual feasibility says the sum on the 2 endpoints should be at least 1. So to figure out what we need to scale by, we ask the question, okay, how small could the sum of the Q values be on a given endpoint? And then we have to scale by the reciprocal of that. This shows that the sum of the Q values might be only 1/2 in the current scheme. So we have to scale up by 2. Okay. So that's the bad news. The good news is this is a bad example for our particular analysis. Okay, so for our approach on this board. So it's a bad example. It's a bad example for idea number 1, but it's not actually a very bad example for the water level algorithm. It's not optimal here, but it's not actually doing all that badly either. So value of the water level solution. Okay, well this one's fully matched, this one's fully matched, this one's matched up to 5/6, and this one's not matched at all. Whereas opt is 4. But this is a lot bigger than 2, right? This is close to 3, okay? So the ratio in this example is certainly bounded away from 1/2. Point being, it still opens the door that the water level algorithm is actually a good algorithm, and we just haven't been smart enough yet to prove it so, okay? So all we know is we need one more idea if, in fact, we're going to prove a better bound for this algorithm. But again, if we believe in the algorithm, we should just keep the algorithm fixed and ask, how can we be smarter just in the analysis? Okay? So any questions so far? All right. So idea number 2. So now, if we're feeling kind of lazy or uninspired, we might ask ourselves, okay, what's like the minimal change we can make to the last idea so that it's not obviously broken, okay? And there's not a unique answer to that, but what's tempting is to keep the algorithm the same, to keep the approach of, using a dual feasible solution the same, and to keep this sort of goal, of trying to sort of construct these Q values so that scaling, hopefully gets us dual feasibility. And the one thing which is tempting to change is that we were doing an equal split, always, between the 2 endpoints of an edge. So idea number 2 is when we increase the extent to which an edge is matched, we're still going to split that delta between the endpoints, but not necessarily 50-50. Okay? So unequal split between QV and QW. And for motivation, just think about our bad example, all right? So remember, the algorithm is fixed, okay? So we're not thinking about, the algorithm is going to keep doing the same thing on the same example. The only thing we're thinking about modifying is, who gets what Q value. And notice, here on the right-hand side, this southeast vertex, it never participates in any edge getting increased at all. So unless we do something really crazy and unnatural, that southeastern vertex is going to get a Q value of 0, because all of the edges around it are 0. So if we're going to beat 1/2 using this kind of approach, we need to make it so that the southwest vertex, at the end of the day, winds up with a Q value bigger than 1/2, okay? That's what's going to need to happen to beat 1/2, okay? It's not clear it's possible, but if it's possible, it's by making sure that southwestern vertex has a final Q value bigger than 1/2. And that obviously with equal split, we're stuck with 1/2, because you only get filled up to 1. So you're not going to get more than 1/2 with equal split. So evidently, we need to at least sometimes more aggressively give it to one of the two endpoints of a vertex, okay? And the way we're going to do it is we're going to be more aggressive with how much of the split you get as you get more and more full, okay? So as a vertex on the left-hand side gets more full, increase its Q value faster, okay? So when a vertex on the left-hand side is empty, at the end of the day, we'll see that it actually gets less than a 50-50 share. But by the time it's like totally full, it's getting basically 100% of the share. That's what's going to happen, okay? And again, what's the motivation? The motivation is because we want it in this case that you get filled up on the left-hand side. Even if you have these vertices on the right-hand side, which Q value 0, you still are better than a factor of 2 close to dual feasibility, okay? So that's the idea. Now, it's a pretty vague idea. At equal split, at least we knew what we were talking about, 50-50. Unequal split, that could be anything. Right, so how do we pick? Moreover, this idea suggests that actually we're not just going to pick some fixed split. It's not like we're going to change 50-50 to 70-30. Okay, and it's easy to convince yourself that doesn't work. So we actually need the split to change as a function of how full the vertices on the left-hand side are, as a function of their current water level. And it's very hard to know how you should, define this split, like what's going to lead to a good algorithm, if anything. So the approach we're going to do is we're just going to sort of do a generic analysis of the water level algorithm, parameterized by the way in which we're splitting a primal increase amongst these Q values. So for the moment, we're just going to fix a function for discussion from 0,1 to 0,1, which should be non-decreasing, okay? So what's the interpretation of G? So I'm going to erase the primal dual pair, but the one thing to remember from the primal dual pair is just the dual feasibility, okay? The dual feasibility requires the sum of the prices on the two endpoints is at least 1 for every edge. This is the thing to remember. Okay, so G is going to be our splitting function, and it's going to specify what fraction of a delta increase goes to each of the two endpoints, and it's going to depend on how full the left endpoint is, okay? So when increasing the fraction on some edge by some infinitesimal amount, dz, and with the current water level, yv, so remember this is just the sum of the fractions on the incident edges. Okay, so getting more full just means your yv is closer to 1. The plan is to increase qv by G evaluated at the current water level, dz. So this is non-decreasing or increasing. So this is reflecting the point that as a vertex on the left gets more and more full, closer and closer to 1, we're going to aggressively give it more and more of the split. That's what G non-decreasing means. And then we want to give the balance to the right-hand side node. Okay, so GW goes up by 1 minus G of YV dz. Okay? So for example, if you really wanted, you could set G to be the constant function 0. That's going to result in only the vertices on the right-hand side getting positive Q values. Everything will go to the right-hand side. If you wanted, you could set G equal to 1. Okay, that'll give you all the Q values on the left-hand side. If you set G to be the constant function 1/2, that's saying always do an equal split. So that corresponded to what we were doing before, setting G to be the constant function 1/2. Okay? All right, so here's where we stand. So you should be clear on the algorithm. The algorithm hasn't changed. Water level. We're trying to be smarter about analyzing it. How are we trying to be smarter? By allowing sort of varying splits. We're parameterizing that by a function. You should agree that for any choice of G, we get a well-defined, a good, well-defined set of Q values at the end of the algorithm. Remember, the goal is to get for every edge, VW, QV plus QW to be as large as possible. We need at least 1 for dual feasibility. So we want to get as close to 1 as possible before scaling up. And what should not at all be clear is, how to think about G and like what G might be a good G. Okay? So we're just going to do a generic analysis and then solve for the best G. But that's the approach. And so this is the last idea we need. So it turns out if we choose G and just so, we're going to be able to prove a better than 1/2 bound for water level. Okay? Actually, an optimal bound for water level. Okay? Let me just point out that, again, by construction, the value of the water level solution is again equal to the sum of the Q values. Okay? So just by construction. We maintain this inductively at all times. Whenever we increase the value of the fractional matching, we increase the sum of the Q values by the same amount. Okay? So the whole trick is to understand how to pick G so that for every edge, the sum of the Q's is as close to 1 as possible. Okay? Is everyone clear on where we are? So G denotes our splitting schedule. We want to solve for the best G. What does the best G mean? It means the sum of the Q values on the endpoints of every edge is big. Big means close to 1. Okay? And particularly we want it to be bigger than 1/2. Okay? Because then we scale by less than 2, and we get a better than 1/2 competitive ratio. Questions? All right, so analysis. And again, this is going to be sort of generic with respect to the choice of the function G. And then once we do our analysis, we'll get some guidance about what G is going to give us a good competitive ratio. All right, so fix an edge. And again, remember, all of this is in hindsight, so the whole graph has showed up. Okay, so we know the whole graph. It's just in the analysis. Fix an edge that showed up. What we want to do is we want to lower bound. So goal, lower bound QV plus QW. This is what we want to be close to 1. Certainly bigger than 1/2. Okay? So we're going to look at 2 cases. The 2 cases correspond to the 2 ways in which this processing of a new vertex can end. Okay, so remember, a vertex shows up on the right-hand side. One of 2 things can happen. Either it successfully distributes its entire unit of flow, that is, it's fully fractionally matched, or the only way it can fail to distribute everything is if all of its neighbors are totally full. That is, all of its neighbors are themselves fully matched. So those are the 2 possibilities. Let's start with the possibility that this vertex on the left is full at the end of the water level execution. And again, full just means that the water level YV, defined like it is up there, is equal to 1. So we want to lower bound the sum of the Q values of the endpoints. Well, I erased it, but you can still sort of see here an issue is that for all we know, QW is 0, okay? So this could be 0. So we kind of want our analysis to work, so we're going to do a very crude approximation here. We want to lower bound the sum of the Q values, but for all we know, QW is 0, so let's just lower bound the left-hand side Q value. And actually, this is very easy to write down as a function of our choice of G, okay? V, by assumption, V is totally full at the end of the algorithm. Okay, so it's totally filled up. G specifies, as a function of how full it is at a given time, what share it's getting of the current increase. Okay, so think about it from V's perspective, right? First it gets filled up to a fifth, then it gets filled up to 2/5, then it gets filled up to 4/7. You know, this happens in stages, but it's all kind of continuous. So its level gradually goes from 0 to 1 in a continuous way. And in any given level y, G of y is the instantaneous fraction of the increase that it's getting at any given time. So integrated over the course of the whole algorithm, over the whole lifetime, what is the Q value going to be? Well, we just integrate over all of the water levels that this vertex ever has, and again, it goes gradually from 0 to 1. And so that's going to be dz. And at a given current level, dz, G of z, by definition, is its split of the current increase. Okay? So this is just by the definition here. So for example, when G is the constant function 1/2, like we had before, we're going to find out that when a left-hand side vertex is full, it has a Q value of 1/2, which indeed is exactly what happened previously. Okay? In general, what's its final Q value if it's full? What's the integral of G over all of its water levels between 0 and 1? So any questions about that? So again, you should have no sense for whether that's a big or a small number. It's obviously going to depend on G. Right? So remember, we want that to be big. We're trying to lower bound. We want this to be close to 1. So the bigger G is, the better. But that number will be big or small depending on whether G is big or small. Okay? But do you agree with this inequality? In particular, do you agree with this equation? Okay, that's kind of by definition of our analysis approach. Any questions about that? Okay. So again, just for a given choice of G, this is just going to be the number you see on every left-hand side vertex which is full. It used to be 1/2. Now we're hoping it's going to be bigger than 1/2. Okay? All right. But this isn't the only case. If this was the only case, we'd be done, because we could just set G to be the constant function 1. Okay? We'd have a great lower bound. It would be at least 1, way bigger than 1/2. But this isn't the only case. Case 2 is that at termination, V is not full. Okay? Obviously, that's the other case. Now notice, if this left-hand side vertex V is not full, if it has space remaining, it must be that its neighbor on the right-hand side, W, got rid of its full unit of flow. Why? Well, if W still had flow left and V still had room, the water level would have sent more water on that edge. Okay? So again, it's sort of a maximality property of the water level algorithm. So if V is not full, then W is empty. So W sent all its water. Okay? All right, so good. So what we're going to do here is we're going to give an estimate, a lower bound on W's Q value. Okay? So in our bad example, the reason we had a bad Q value on the right-hand side is because the vertex wasn't matched to anything. So now we're thinking about a vertex W on the right-hand side, which is fully matched. So it better have a non-trivial Q value. Okay? All right. So here's where we use the key property. So the key property here. So remember what the key property says. The key property says, consider a vertex on the right-hand side. Consider any of its neighbors on the left-hand side. Suppose the final level of that water level of some neighbor on the left-hand side was, y. Then, whenever W was sending water to anybody, it was sending it to a container that was carrying Y or less units of water, okay? So in other words, the final level of any neighbor of W is an upper bound on the level at which any container was when it was injecting flow to it. So we're going to use that property now to give a lower bound on QW. So, what's the lower bound? All right, so here's what it's going to be. Okay. So remember, G we picked to be non-decreasing, so the more full something on the left-hand side is, the more bigger split it should get. So 1 minus G is non-increasing. And so therefore, what does that mean? Well, whenever W was sending any of its water, remember it was sending it to something with current level at most, the final level of any of its neighbors, in particular of Y sub V. So W's share of split was at least 1 minus G of Y sub V. Okay? So this is by the key property. So again, just to recap, we fixed some edge, V comma W. We're looking at the case where V is not full and W got rid of everything. And we're trying to say lower bound the Q value of this full vertex W on the right-hand side. So how do we do that? Well, we have this key property which says, well, look, suppose on this edge that we're looking at, the container on the left ended up only 80% full. The key property says that whenever the vertex W was sending flow to anybody, it was to someone who was at most 80% full. We're trying to lower bound the Q value that W gets. So the worst case for this lower bound is that whenever it sent flow to anybody, the level was as high as it could have been 80%. Okay? So that's all this is saying. So this is 0.8. So if it's 80%, this is the share of the increase that goes to the left-hand side vertices. W gets the balance. Okay? So again, we're using that whenever it sent anything, it sent it to a level that was at most Y sub V, and then we're using the G is non-decreasing. 1 minus G is non-increasing. Okay? So that gives us the lower bound. All right, any questions about that point? That's really where the algorithm and analysis come together the most tightly. Okay, if you believe this, we're basically home free. Okay. All right, so what does this mean? So what's the accumulated total, the final Q value of this vertex on the right-hand side? Well, again, remember it winds up full, right? So this is case 2. V is empty. That can only happen if W is full. So we can, again, integrate over its entire lifetime, all the levels it ever took on between 0 and 1. And we know that at any given time in its lifetime, it was getting at least a split of 1 minus G of YV, where again, V here is just some neighbor on the left, YV is its final level. DZ, sorry. Okay? This is a very easy integral. Right? The integrand does not depend on the integrating variable. So this is just 1 minus G of Y sub V. Okay? And so that means in case 2, so summarizing, in case 2, QV plus QW, well, first it's the contribution from QV. QV, so this, remember in case 1, this was 1. Now it's going to be less than 1. But we can still integrate from 0 to the final water level of V of its share of the split. So this is the contribution. This is exactly Q sub V. And then we have our lower bound on Q sub W. Okay? So let's call this number 2, and this thing up here number 1. Okay? So again, just to make sure you don't lose the forest for the trees, what are we trying to do? We're trying to prove that these Q values are pretty close to being dual feasible. What does that mean? It means the sum of the Q values on each end, on the endpoints of any edge should be pretty big, close to 1. Okay? So quantity 1 is a lower bound on the sum of the Q values of the endpoints of an edge in the case where the left-hand side vertex was full. Okay? Yeah, the left-hand side vertex was full. So this is a lower bound on the sum of the Q values in one of the cases. That is a lower bound on the sum of the Q values in the other case, where the left-hand side container is not full and the right-hand side container got rid of all of its water. Okay? So what do we want to do? So again, G is still a free parameter. So we want to choose G so that both 1 and 2 are big, as close to 1 as possible. Okay? Again, we want to say the sum of the Q values of the endpoints of every edge is high. Some of our edges will fall into case 1. Some of our edges will fall into case 2. So we need to make both the expressions 1 and 2 large simultaneously. If all we wanted to do was make 1 large, we'd just choose G to be the constant function 1. If all we wanted to do was to make 2 large, we'd just choose the constant function G equals 0. Okay? So the tricky part of the analysis is balancing this perfectly, getting both of these numbers to be big simultaneously. Notice that if we choose G to be 1/2 like we were doing before, we would at least prove that 1 is at least 1/2 and that 2 is at least 1/2. Okay? But we'd like to do better. Okay, so we want to get better than 1/2 for both with a suitable choice of G. Okay? So any questions about that? All that's left is to solve for the best G, which actually isn't as hard as it sounds. It's not that bad. Okay. All right, so to do, solve for G to maximize. Remember, we want to get these numbers as close to 1 as possible. To maximize the minimum of 1 and 2. And let me also point out that when I say 2, actually 2 is a whole bunch of different things because there's a free parameter y sub v on the right-hand side. Remember, y sub v is just however full the left-hand side vertex wound up at the end of the algorithm. Somewhere between 0 and 1, we have no control over what. So really, I mean we want to maximize the minimum of 1 and 2, even for a worst case choice of yv in 0, 1. Okay? So for all y sub v in 0, 1. Okay. So this may sound kind of intimidating, right? Because you have this free parameter g. G is a function, right? From the interval to the interval. There's a lot of functions from the interval to the interval. So how do you know which one to use? Well, one kind of non-rigorous but useful guiding principle is that, you know, in optimal algorithms especially, which this one is, as we'll discuss, they often have the property that kind of, you know, your loss is perfectly spread. Your errors are just perfectly balanced across all possible cases. There's no slack in the error in any case. So if you think that's going to be true here, what it suggests is saying, well, let's see if we can find a function g so that 1 equals 2. And actually 1 equals 2 no matter how we choose the free parameter y sub v in 0, 1. Okay? So again, think of one as sort of one condition. Think of 2 as actually an infinite number of conditions, one for each choice of y sub v in 0, 1. Okay? So the trick, or the idea, and again, this is often super helpful in analysis, is try to equalize all of the different cases. So that says in particular, maybe we should choose g so that that expression in 2 is just a constant, independent of the choice of yz in 0, 1. Okay, so this is just going to be a guess. But again, the seasoned analyst often makes use of this guess. So we're going to guess that for the g that we really want, 2 is a constant. Independent of yv and equal to 1. Okay? Now, first of all, it's not clear a priori that there exists a g with these properties. Okay? There's no guarantee of that unless we actually try. Secondly, even if we do find such a g, it's not immediately obvious that that's going to be an optimal g. Okay? So this is a guess and check approach. Okay? We just need sort of a principled way to explore the space of g's. Balancing error seems like a good principle, and it's going to give us much simpler equations to solve. Okay? All right, good. So assume that there is a g satisfying all these properties. We don't know if there is one, but assume there is one. What must it look like if g really does exist? Let's just focus on the aspect where we want 2 to be equal to a constant, no matter what y sub v is. Or, put differently, if we think about expression 2 as a function of y sub v, it should be a constant function. That is, it should have a derivative of 0. So if so, if we take the derivative of the expression 2 with respect to the variable y sub v, that should be 0. Okay? So if there's a g that makes that constant for all yv, then of course we differentiate with respect to yv, we get 0. Okay? All right. Well, now actually, this is really not that hard to understand. Right, so we're differentiating 2 with respect to y sub v. So the derivative just cancels that integral. And then, of course, the 1 disappears and we get a g prime. Or if you prefer, moving this over, g equals its derivative. Now, it's been a long time since I took ordinary differential equations, long time. Ironically, I think I took it in this very classroom. I don't remember almost anything. The one differential equation I remember is the one about a function being the same as its derivative. Right, so what's the solution? E to the x, okay? So again, if in fact there's a function g which makes that a constant, then it's got to satisfy this, so it's got to be an exponential function. Okay? So gy equals e to the y. Actually, if you think about it, there is one free parameter here, which is we can have an arbitrary positive constant k in front. And no matter what k is, it'll satisfy this. Okay? So our first guess actually really narrowed down the space of g's to look at. Right? We used to have all functions. We used to have like an infinite dimensional free parameter. Now we just have one free parameter, namely the coefficient k, in front of e to the y. Okay? Good. So, how do we decide how to pick k? Well, so now we're going to use the part of the guess where we want to equalize 1 and 2. Okay? So remember, we want both 1 and 2 to be big. 1 is big when g is big. If you stare at 2 a little bit, you realize 2 is big when g is small, because when g is small, this part is big. Okay? So how do we balance those? How do we pick the optimal k that makes them exactly the same? So let's plug in. Okay, so let's, again, k is a free parameter. Let's plug in this function g into 1. Okay, what do we get? All right, so 0, 1, k e to the y, e to the z rather, dz. Okay, so pull the k out in front, which is a constant. Integral of e to z is e to the z, so 1 to the 0 equals k of e minus 1. Okay, so we just turn the crank. That's what we get. And again, notice that the bigger k is, the better from the perspective of expression 1. And again, we knew that. We knew the bigger g's were a bit better for 1. So how about 2? So now we're integrating the same thing, but not from 0 to 1, but from 0 only to y. But then we also have this 1 minus g of y. So that translates to 1 minus k to the ey. So the same computation as before tells us that this equals k times e to the y minus 1. No longer e minus 1, but e to the y minus 1. And we see that this k e to the y cancels with that k e to the y. So we're left with, let's see.
Be a plus.
Yeah, something's fishy, yeah. That should be a plus, right? Yeah. So we're left with 1 minus k, okay? So notice this derivation is true no matter what y is. Okay, I chose y arbitrarily in 0, 1, and I got a number 1 minus k that was independent of y. But of course, we knew that was going to happen. We chose g exactly so that this quantity 2 would be independent of y. Okay? And as we see, for this to be big, we want k to be small. Okay? And we already observed that 2 is more prone to be big if g is small. So now I just set these equal. So setting 1 equal to 2, what do we get? So move the k over, blah, blah, blah. Should be 1 over e. Okay? So I just equalize those two. Solve for k, get 1 over e. Plugging back into g, our function g, remember g was k times e to the y. So that gives us g of y is e to the y minus 1. Okay? And again, so just thinking back about the original semantics of g specifies what fraction of the share does the left-hand side vertex get as a function of how full it is. So when you have a vertex on the left-hand side which is totally empty, like at the beginning of the algorithm, that corresponds to y equals 0. And so g of 0 is 1 over e. So at the beginning of the algorithm, when you first start raising, again remember, this is just in the analysis. Our algorithm has stayed the same this whole time. But in our analysis, at the beginning of the algorithm, when we're increasing edges and we have these empty containers, we're actually doing an unequal split that favors the right-hand side. Okay? 1 over e on the left, 1 minus 1 over e on the right. This is going to evolve as y goes from 0 to 1. This will become a more and more aggressive split in the left-hand side vertex's favor. And when y is all the way up to its maximum about 1, then this is actually going to be equal to 1. Okay, so 100% of the split is going to be going to the left-hand side vertex at the time that it's getting totally full. Okay? So this is interpolating between unequal splits favoring first the right-hand side, then the left-hand side, as a function of the fullness of the left-hand side vertex. Okay? All right, and so now what is the magic number? So what is 1 and what is 2? So 1 equals 2 equals 1 minus 1 over e. Okay? This is roughly 63.2%. Okay? So it's noticeably better than 1/2. Okay? And so remember, now we're done. Okay, because this was the whole game. The whole game was to define the Q values in a way that for every edge, the endpoints are guaranteed to be close to 1. Why? Because then we just take those Q values, we scale it up by the reciprocal of this, so E over E minus 1. That gives us a dual feasible solution, which in turn is an upper bound on the maximum possible matching. So the water level algorithm outputs a fractional matching with at least this fraction of our upper bound on the optimum. Okay? So that completes the analysis. So 2 comments. So first of all, as I said, you can have a randomized algorithm for the integral case, where basically the probabilities sort of simulate what's going on with the fractions. And so you can again get a randomized algorithm for online bipartite matching with a 63.2% competitive ratio. Problem set number 4 will walk you through on that. Now, as far as, could we be even smarter? Could we keep the algorithm the same and get a better competitive ratio? Or maybe we could have a smarter algorithm and get a better competitive ratio. Well, the last problem on problem set number 3 is actually a proof that no algorithm, necessarily randomized or otherwise, can beat 63.2% for online bipartite matching. Okay, so the water level algorithm actually, at least in the worst case, is the absolute optimal online algorithm for the problem. Next week we'll start talking about NP-complete problems. Have a good weekend.